Hello everyone again, and Bismillah. In this video we are going to simulate the derivative and proportional controller that we have previously designed. As usual, we start by putting or writing down the transfer function of our plant. We have already memorized that transfer function. It's 1, 3, and 2. And now we add the reference as well, which is a step function. And we'll not change its settings. Let it be on its default. We will add the summation block as well in order to form the closed loop or the negative feedback closed loop system. We will take a measurement from the output, then we will change this to have a minus sign, negative sign in here. Okay, now we will add a scope in order to investigate what's going on with the output. Sorry, it's a scope. So now we have our system ready without adding any controller. But we know that we have designed a PD controller. And in order to add that PD controller, we will get rid of this line and instead introduce the proportional controller, which is a simple gain. And we selected it to be 20. Then we will add the second thing. The transfer function of our PD controller is 20 plus 3.5 times S. Now, 3.5 is another gain. So we will add another gain. And this gain's magnitude is 3.5. So how are we going to represent S? Now, S is simply a derivative action. So we may add a derivative block in here. And this derivative block simply represents S. Now, this is not a causal controller. I'm not going to delve into the details of the control theory about causality and those things. But you may know that this controller configuration is not valid in real life because it's not a causal controller. We do not, in order to achieve this certain derivative action, we have to know something about the future, while we do not know anything about the future. You know that the derivative defines the slope of the error in here, but we do not know the future values of our error. So this is not causal. But we may, we may overcome this problem of causality using other configurations. I'm not gonna talk about this in this video, maybe in upcoming videos, inshallah. Now let's assume this is our controller. We will add a summation block because the controller is the sum of these two terms. So we have this, and we also have this. Then both of them are actually connected in here, and we have to connect these branches. Now this is how our controller looks like. Let's have a look at here. Okay, no problem. Now let's just run this controller and look at the response of the system with a PD controller. Yeah, it's taking some time. Okay. Now you see that at 1 we already have the same. The system started to make some response, started to respond to our input or reference. So let's just have a look at the properties of this response. Let's wait for them. They are coming out right now. So the rise time is already achieved. We have a rise time less than half a second, and this is actually very good. We also have a very, very good amplitude at steady state. It's 0.9. It's almost 1. We may actually manually tune the parameters in order to get a better amplitude. When it comes to the overshoot, let's just open this. Yeah, we can see that the overshoot is 2.5%, which is half of 5%, which was the demand of the system. We have achieved the total overshoot that we wanted. However, the system is still having some kind of a steady state error. Its steady state error is almost 0.1, and we would like the system to have almost no steady state error. This can be achieved using manual tuning. We can manually tune these parameters. For example, let's just raise this. Let's put it as 40. There was that certain formula that we had to follow in order to select the PD controller. Now, if we have 40 as our KP, then the KD will be 1.38 times the square root of 2 plus 40 minus 3. And this gives us 5.94. So 5.94. Now let's just have a look at the new response. Is it better? Is it worse? We will have a look. And yeah, we can see that the steady state response has increased a lot. It's a very, very good steady state response. Actually, the error is almost 0.5, meaning that it's almost 5%. Sorry, it's 0.05, meaning that it's almost 5%. it's an acceptable error for us right now. We may have another configuration, another controller, in order to get to almost totally get rid of this steady state error. So thank you for listening, and this was our video today, and see you again later.